In the vast expanse of our cosmos, there exists a dance so delicate, so subtle, that only the most sophisticated instruments can detect its graceful movements. Picture this. Somewhere in the infinite darkness of space, a star exhibits an unusual behavior. Instead of following a straight path across the heavens, it performs a gentle zigzag motion through the cosmos. This seemingly insignificant wobble holds within it one of the universe's most profound secrets, the presence of distant worlds orbiting far beyond our solar system. This cosmic waltz tells us an incredible story of discovery and innovation. Today's astronomers have become true cosmic detectives, wielding a powerful technique called astrometry to uncover planets that lie light years away from Earth. Their method is quite remarkable. Imagine being able to detect an invisible dance partner simply by watching the visible dancer's movements. This is precisely what astronomers do when they use astrometry to discover exoplanets. They observe the subtle ways stars move in response to the gravitational pull of their unseen planetary companions. The beauty of this method lies in its elegant simplicity, though its execution requires extraordinary precision. Think of it as trying to spot a firefly's shadow from across a continent. Every slight stellar wobble, every minor deviation from a star's expected path could signal the presence of an undiscovered world. These minute movements, often measuring mere millionths of a degree, have opened up entirely new horizons in our understanding of planetary systems beyond our own. For those captivated by the idea of discovering new worlds, the journey has only begun. Modern astronomy stands at the threshold of an unprecedented era of discovery, where each new observation might reveal another piece of the cosmic puzzle. Through advanced telescopes and increasingly precise measurements, we are uncovering the true diversity of planetary systems that populate our galaxy. From massive gas giants to small rocky worlds, each discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? This story of celestial detection represents one of humanity's greatest scientific achievements. Our ability to find worlds we cannot directly see, orbiting stars so distant that their light takes years to reach us. It's a testament to human ingenuity and our relentless pursuit of knowledge about the cosmos that surrounds us. For those fascinated by the prospect of discovering new worlds and unraveling the mysteries of our universe, this journey through the science of astrometry promises to be an enlightening adventure. Join us as we explore how astronomers have transformed themselves into cosmic detectives, using the ballet of the stars to reveal the hidden planets that dance among them. Astrometry stands as one of astronomy's most venerable techniques, dating back to the earliest days of celestial observation. This ancient practice, which began with careful measurements of star positions in the night sky, has evolved into one of our most sophisticated tools for discovering worlds beyond our solar system. To truly appreciate the genius of this method, let's explore its fundamental principles through a simple yet powerful analogy that brings cosmic mechanics down to Earth. Picture a father playing with his child in a park, spinning them around in circles with outstretched arms. This familiar scene perfectly illustrates the principles at work in planetary systems. Just as the father represents a star and the child represents an orbiting planet, both participants in this cosmic dance aren't simply rotating around a fixed point. Instead, they both orbit around what physicists call their common center of mass. The father, being much more massive, makes smaller circles, while the child traces larger ones. But both are in constant motion. This same principle operates on a cosmic scale. When we observe stars that host planetary systems, we're witnessing a similar dance, though on a vastly larger stage. Just as the father slightly sways while spinning the child, a star wobbles as its planets orbit around it. This stellar movement, though incredibly subtle, provides astronomers with clear evidence of planetary companions. Understanding stellar motion requires careful consideration of two distinct components. First, there's the star's proper motion, its natural path through the galaxy, which typically appears to us as a relatively straight line across the sky when observed over human timescales. Then there's the additional wobble motion superimposed on this path, caused by the gravitational influence of orbiting planets. This wobble creates a distinctive pattern. Rather than moving in a straight line, the star appears to weave back and forth as it travels through space. The precision required to detect these movements is staggering. Imagine trying to spot the slight tremor in a lighthouse beam from hundreds of miles away. This gives you an idea of the incredible sensitivity needed for astrometric measurements. Modern telescopes must be capable of measuring angular distances smaller than a human hair viewed from several miles away. This delicate dance between star and planet produces a unique signature in our observations. When astronomers plot the position of a star over time, they can identify these telltale oscillations. A star without planets will show only its proper motion, moving in a relatively straight path against the background of more distant stars. However, a star hosting planets will display an additional periodic wobble superimposed on this straight-line motion, creating a pattern that resembles a sine wave when graphed over time. What makes this method particularly powerful is its ability to reveal information not just about a planet's existence, but also about its characteristics. The amplitude of the stellar wobble correlates directly with the planet's mass. Larger planets cause more pronounced stellar movements. Meanwhile, the period of the wobble tells us about the planet's orbital period, allowing astronomers to determine how long it takes to complete one orbit around its star. The beauty of astrometry lies in its direct connection to fundamental physical principles. Unlike some other planet detection methods that rely on secondary effects, astrometry directly observes the gravitational dance between star and planet, providing us with a window into the mechanical workings of distant solar systems. This deep connection to basic physical laws makes astrometry not just a tool for discovery, but also a powerful means of understanding the dynamics of planetary systems across our galaxy. The fundamental physics underlying astrometric detection of exoplanets rests upon one of the most elegant principles in science, Newton's law of universal gravitation. This law, which tells us that every mass in the universe attracts every other mass, with a force proportional to their masses and inversely proportional to the square of the distance between them, forms the cornerstone of our understanding of planetary motion. When we apply this law to star-planet systems, we discover something fascinating. Stars don't simply sit still while planets orbit around them. Instead, both the star and its planets orbit around their common center of mass, a point known as the barycenter. This center of mass acts as the fulcrum of the cosmic balance between the two bodies. Think of it as the average position of mass in the system, weighted by the mass of each object. In our own solar system, for instance, the barycenter of the Sun-Jupiter system actually lies slightly above the Sun's surface due to Jupiter's considerable mass. The mathematics of this dance reveals a crucial relationship. The more massive the planet, the more pronounced the star's movement will be. This creates what astronomers call a reflex motion in the star. A giant planet like Jupiter will cause its star to execute a larger wobble than a small Earth-sized planet would. The exact size of this wobble can be calculated using the equation for the center of mass, R1m1, R2m2, where R1 and R2 are the distances of each object from the center of mass, and m1 and m2 are their respective masses. This simple equation helps astronomers predict just how much a star should move if it's hosting a planet of a given mass. The precision required to detect these stellar movements is nothing short of astronomical. The wobble of a star caused by an Earth-sized planet at a distance similar to our Earth's orbit would result in angular movements of just microseconds of arc. That's about the same as trying to measure the width of a human hair from 100 miles away. To put this in perspective, 1 arc-second is 1/3600th of a degree, and we're talking about measuring movements thousands of times smaller than that. This is where modern technology becomes crucial. Today's telescopes, particularly space-based observatories like Gaia, can achieve precisions of a few micro-arc-seconds. This incredible precision allows us to detect the minute gravitational effects of planets on their host stars. For comparison, detecting a Jupiter-sized planet around a Sun-like star requires measuring angular movements of about 500 micro-arc-seconds, while finding an Earth-like planet would require detecting movements of less than 1 micro-arc-second. The relationship between a planet's mass and its star's wobble creates an interesting observational bias. Massive planets are easier to detect than smaller ones. However, this is just one part of the equation. The distance of the planet from its star also plays a crucial role. A planet orbiting closer to its star will complete its orbit more quickly, making its effects easier to detect over shorter observation periods. However, the amplitude of the stellar wobble will be smaller due to the shorter lever arm of the orbital radius. This brings us to an intriguing question for aspiring planet hunters, which would be more challenging to detect: a massive planet orbiting far from its star, or a smaller planet in a closer orbit? The answer involves a complex interplay of orbital period, stellar wobble amplitude, and the duration of our observations. While the massive distant planet might create a larger wobble, its longer orbital period means we'd need to observe it for many years to detect a complete cycle. The smaller, closer planet might have a smaller wobble amplitude, but its shorter orbital period means we could observe multiple cycles more quickly, potentially making it easier to confirm its existence through repeated observations. Understanding these physical principles not only helps us detect exoplanets, but also allows us to determine their properties. By carefully measuring the amplitude and period of a star's wobble, astronomers can calculate both the mass of the planet and its orbital characteristics, giving us a window into the diversity of planetary systems throughout our galaxy. Astrometry, while powerful in principle, faces several formidable challenges that have historically limited its effectiveness in exoplanet detection. These challenges have driven remarkable technological innovations, ultimately leading to breakthrough discoveries that continue to reshape our understanding of planetary systems. The first and perhaps most significant challenge lies in the incredibly subtle nature of the stellar movements we're trying to detect. When a planet orbits a star, the resulting stellar wobble is minuscule, often comparable to measuring the thickness of a human hair from across an entire city. This challenge is compounded by the fact that stars aren't perfect point sources of light. They're complex, dynamic objects with their own internal movements and surface features that can mask or mimic planetary signals. Long-term observation requirements present another substantial hurdle. To confidently detect a planet, astronomers need to observe multiple complete orbital cycles. For planets with orbits similar to Earth's, this means maintaining precise measurements over several years. During this extended period, every aspect of the observing system must remain incredibly stable. Even the smallest change in instrumental calibration or observing conditions can introduce errors that mask the subtle planetary signals we're seeking. Atmospheric interference has historically been one of astrometry's greatest enemies. Earth's atmosphere is in constant motion, causing starlight to twinkle and dance, a phenomenon astronomers call seeing. These atmospheric distortions can easily overwhelm the tiny angular movements we're trying to measure. Even on the best observing sites on Earth, atmospheric turbulence can introduce errors orders of magnitude larger than the planetary signals we're trying to detect. Enter the Gaia Space Telescope, a technological marvel that has revolutionized astrometric measurements. Launched by the European Space Agency in 2013, Gaia operates from the Lagrange point L2, about 1.5 million kilometers from Earth, free from atmospheric interference. This strategic position, combined with its revolutionary design, has transformed what's possible in astrometric measurement. Gaia's precision is unprecedented in the history of astronomy. The telescope can measure stellar positions with an accuracy of up to 7 microarc seconds for the brightest stars, equivalent to measuring the width of a human hair from 1,000 kilometers away. This extraordinary precision comes from a combination of innovative engineering solutions, including a stable thermal environment, sophisticated optical systems, and advanced data processing techniques. What truly sets Gaia apart is its comprehensive approach to stellar observation. Rather than focusing on a small number of target stars, Gaia is conducting a systematic survey of over 1 billion stars in our galaxy. This massive sample size not only increases the chances of detecting planetary systems, but also allows astronomers to study planetary occurrence rates across different stellar populations. The telescope repeatedly observes each star an average of 70 times over its mission, building up a detailed picture of any periodic movements that might indicate the presence of planets. Perhaps most exciting is Gaia's ability to detect multiple planetary systems. Traditional astrometric measurements often struggled to disentangle the signals from multiple planets orbiting the same star. Gaia's precise measurements and long observation timeline allow astronomers to identify the complex orbital dynamics of multi-planet systems. This capability is crucial for understanding how planetary systems form and evolve, as most stars are now thought to host multiple planets. The innovations embodied in the Gaia mission have opened new frontiers in exoplanet detection. By combining unprecedented measurement precision with comprehensive sky coverage and long-term stability, Gaia is helping us build a much more complete picture of planetary systems in our galaxy. The telescope is expected to detect thousands of new planets, particularly massive planets in long-period orbits, a population that's been largely inaccessible to other detection methods. These advances in astrometry aren't just about finding more planets, they're about understanding our cosmic context. Each new planetary system we discover helps us understand how unique or common our solar system might be, bringing us closer to answering fundamental questions about our place in the universe. As we continue to push the boundaries of precision measurement, future missions building on Gaia's innovations promise to reveal even more secrets about the diversity of worlds that populate our galaxy. The history of astrometric discoveries tells a compelling story of scientific persistence and technological triumph. One of the most famous early cases was the search for Sirius B. In 1844, Friedrich Bessel noticed that Sirius, the brightest star in our night sky, exhibited a peculiar wobble. This observation led to the prediction of a companion object, later confirmed to be a white dwarf, Sirius B. While not a planet, this discovery demonstrated the power of astrometry to detect unseen companions through their gravitational effects on visible stars. More recently, astrometry has entered a golden age of discovery thanks to space-based telescopes. The Gaia mission has been particularly revolutionary, providing astronomers with an unprecedented view of stellar movements across our galaxy. One of its most exciting discoveries came in 2020 when it detected a previously unknown Jupiter-sized planet orbiting a nearby red dwarf star. This discovery was significant because it demonstrated Gaia's capability to find planets in longer orbits than those typically found by other methods. Among the most intriguing recent discoveries is the detection of multiplanetary systems through astrometry. These observations have revealed complex orbital architectures that challenge our understanding of planetary system formation. For instance, Gaia data has helped identify systems where planets orbit their stars in resonant configurations, where the orbital periods of different planets are related by simple numerical ratios. These arrangements provide crucial clues about how planetary systems evolve over time. Looking toward the future, the potential for new discoveries is enormous. Gaia's continuing mission, combined with improved data analysis techniques, is expected to reveal thousands of new planets over the next decade. Particularly exciting is the prospect of finding planets in the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. While current astrometric precision makes detecting Earth-sized planets challenging, future missions are being designed to achieve even greater sensitivity. When compared to other planet detection methods, astrometry offers several unique advantages. Unlike the transit method, which can only detect planets that happen to pass between their star and our line of sight, astrometry can potentially find planets regardless of their orbital orientation. It's also particularly sensitive to planets in wider orbits, complementing the radial velocity method, which works best for planets in closer orbits. Another fascinating aspect of astrometric discoveries is their ability to determine a planet's true mass. Methods like radial velocity can only provide a minimum mass estimate because they're affected by the unknown inclination of the planetary orbit. Astrometry, however, can determine the actual mass of the planet because it observes the two-dimensional motion of the star on the sky. Some of the most remarkable recent findings include the detection of massive planets around young stars, helping us understand how planetary systems evolved from their earliest stages. The discovery of planets around binary star systems, showing how planets can form and survive in these complex gravitational environments. The identification of planets around different types of stars, from tiny red dwarfs to massive giants, revealing how planetary formation varies with stellar properties. The future of astrometric planet detection looks particularly bright, with planned improvements to existing facilities and new missions on the horizon. Next-generation space telescopes promise even greater precision, potentially allowing us to detect Earth-like planets around nearby stars. These future observations could help answer one of humanity's most profound questions: how common are worlds like our own? Perhaps most exciting is the potential for combining astrometric data with other detection methods. For example, when astrometric observations are combined with radial velocity measurements, astronomers can build complete three-dimensional models of planetary systems. This multimodal approach provides a much more complete picture of planetary architectures and dynamics. As our technological capabilities continue to advance, astrometry is likely to play an increasingly important role in exoplanet research. The method's ability to provide precise measurements of planetary masses and orbits, combined with its sensitivity to long-period planets, makes it an invaluable tool in our quest to understand the diversity of planetary systems in our galaxy. Each new discovery brings us closer to understanding our cosmic neighborhood and our place within it. The journey through the world of astrometry reveals one of the most profound truths about astronomical discovery. Even the smallest, most subtle movements in the cosmos can unveil extraordinary secrets about our universe. What began as a simple technique for mapping star positions has evolved into one of our most powerful tools for discovering and understanding worlds beyond our solar system. The elegance of astrometry lies in its fundamental simplicity, the careful observation of stellar motion, combined with the remarkable precision of modern technology. Every tiny wobble we detect, every minute deviation from a star's expected path, potentially signals the gravitational dance between a distant star and its unseen planetary companions. These subtle movements, measured in mere millionths of a degree, have opened windows to countless new worlds and transformed our understanding of planetary systems. As we've explored, the challenges of astrometric detection are formidable, requiring extraordinary precision, patience, and technological innovation. Yet the rewards have been equally extraordinary. From confirming the diversity of planetary systems to revealing the true masses and orbits of distant worlds, astrometry has contributed fundamentally to our growing understanding of our cosmic neighborhood. Each new discovery reminds us that we are part of a vast galactic ecosystem teeming with planets of all sizes and descriptions. Looking to the future, we stand at the threshold of even greater discoveries. As our instruments become more precise and our methods more refined, we move closer to detecting smaller planets, including potentially habitable worlds similar to Earth. The ongoing revolution in space-based astrometry, led by missions like Gaia and its future successors, promises to reveal thousands more planets, each adding another piece to the puzzle of how planetary systems form and evolve. Perhaps most importantly, astrometry teaches us a valuable lesson about scientific discovery. Sometimes the most significant revelations come not from grand, obvious phenomena, but from the patient observation of the subtlest effects. In this way, astrometry embodies the essence of scientific inquiry, the careful, methodical search for truth in the finest details of nature. For those fascinated by the cosmos and the quest to understand our place within it, the story of astrometric planet detection offers both inspiration and promise. It shows us that with persistence, innovation, and careful observation, we can unlock the deepest secrets of the universe. Each new planet discovered through astrometry adds another chapter to humanity's greatest adventure, the exploration and understanding of the cosmos that surrounds us. As we conclude our exploration of this fascinating field, we invite you to remain part of this ongoing journey of discovery. The universe is vast, and every day brings new possibilities for discovery. If you're captivated by these cosmic revelations and want to continue exploring the wonders of the universe with us, we encourage you to stay connected with Exploring the Universe. By subscribing to our channel and activating notifications, you'll be among the first to learn about new discoveries, breakthrough observations, and the latest developments in our understanding of the cosmos. Remember, every time you look up at the night sky, you're witnessing countless stellar dances, each potentially hiding the secret of undiscovered worlds. The universe is waiting to reveal its mysteries, and through techniques like astrometry, we're gradually learning to read its subtle signs.